Hello and welcome everyone to the next event in our webinar series, a presentation by guest speaker Oscar Martinez, professor at the University of Buenos Aires. My name is Matt Kirchner and I will be moderating today's talk. Oscar's extensive career in optics started at Bell Laboratories. He co-founded the startup company Toolkit SRL and is a former fellow of the Optical Society of America. Martinez is a pioneer in ultrafast pulse generation and manipulation with the invention of the prism compressor, the Martinez stretcher, analyses and descriptions of ultrafast pulse forming mechanisms, including Kerr lens mode locking, and the description of space-time coupling upon propagation of femtosecond pulses, among many other seminal publications in the field. We look forward to hearing about how to tame ultrashort pulse shapes in his talk today. Throughout this talk, please feel free to submit any questions you have using the Q&A tool. Oscar will be answering selected questions at the end of the presentation. Now, I'd like to hand the talk off to Oscar.
Okay, great to be here. Thank you very much. And this is a horrible spring shower day we have here in Buenos Aires. I hope you have a better time wherever you are. I was afraid I wouldn't be able to deliver this seminar because we are struggling with a lot of problems in university with a government that wants to shut it down. But fortunately, we were shut yesterday and the day before, but we are open today. So thanks a lot for being there and for whoever hears this after in the recording. So I'm going to talk about femtosecond pulses. When I say ultra short, it's femtosecond pulses. That's below the picosecond. And I targeted this talk to newcomers in the field, to people that have instruments they want to learn how to use, but are not experts in femtoseconds. So I will use cartoon physics and a lot of hand waving to explain the basic physics behind the femtosecond pulse propagations. And I hope experts in the field will enjoy this talk just because they will find new ways to communicate to their students whatever they need to transfer. So first, this is the outline of my talk. I will briefly make a statement of the problem, tell you what we want to talk about, then pulse propagations in one dimension, then go to 3 dimensions where the intuition is not that high, and how that can be used to your favor. Then I will discuss other shaping mechanisms. Finally, references. The reference will be very brief, just a snapshot, so you can just look at them when you stop the video later on. So let's start with the statement of the problem. What I will try to show you here is different experiments where the requirements for the short pulses are different. So it's important to be aware that depending on your experiment, you have to decide what's important and what's not relevant. So here we have a first example. This is my multiphoton excitation microscopy. And what you see here is, for example, this is a ground state of a fluorescent molecules. When the electron is in the high upper state, it will decay emitting a photon here. But if you excite it using 2 photons, like here, then your excitation probability will be proportional to the intensity squared and to the pulse width. So this means that if we look at this graph here, you have a blue pulse profile and a red pulse profile. They both have the same energy. But it's clear that the blue one has a higher intensity, and because of this intensity square dependence, it's very important to keep your pulse as narrow as possible to have all the highest intensity for your best signal. So this is just the first example. Now, if we change the example, we go to a pump and probe experiment. Here you have a pulse that hits your sample and excites it in some manner, and then you use a second pulse delayed by some amount, and this pulse now probes your sample. Now, if you have a pulse like this one I'm showing here that has a satellite pulse, This satellite pulse will confuse you when you are trying to understand your temporal response of your system, because when your probe pulse overlaps with the satellite pulse, that will give a funny signal that it will be difficult to interpret. So this is a different situation. This satellite might not be a killer for a multiphoton process, for microscopy, but it is a killer here. Now, ultra high intensity and pedestals. Let's look at this, 30 joules, 30 femtoseconds. If we focus this down to 1 micron square, you have 10 exawatts per square centimeter. This is a linear intensity versus time profile, and it looks very clean. But when you look at it at the logarithmic scale, you see you have this pedestal here. You have 10 exawatts at the peak per square centimeter. You have 100 terawatts per square centimeter at the pedestal, and that will blast your sample before your pulse gets there. So this is showing that this is an experiment where the high contrast is crucial, very different from the prior experiments. Now, let's look at the different situation. Okay, so now you see this, but this shear pulse amplification is just an example of a situations where you need, well, you have a short pulse coming into a system to an amplifier, and because of the high powers you are going to get, you need to broaden your pulse by factors of thousands of times to avoid the high peak intensity to destroy your system and even destroy by nonlinearities your pulse. After the pulse has been amplified, it has to be recompressed. So now you have a different situation where not only you want to keep your pulse short, but actually you want to broaden it and then afterwards recompress it perfectly. Here are the different situations that you can encounter. There are many applications, and each application has its restrictions and conditioning of your pulse. And that's why I wanted to address to the general problems. And then in your experiment, each person, each researcher has to decide what things you have to keep control and what things are not relevant. So here, now I will discuss first propagation in one dimension because it's easier to gain intuition in one dimension. What you look at the right, you can see that there are many different frequencies that are overlapping and interfering. If you look at the center at t equals 0, you see that all those frequencies interfere incoherently, and that builds up that blue pulse that you're seeing there. In the left, you will see it in a different time scale. What's important is that if you want the shortest possible pulse with the highest intensity, you need all the frequency components that synthesize your pulse to be in phase at a given point of time. And then they just interfere destructively, and that's what builds the short pulse. So, okay, the next one. So the problem, yeah, the next slide. The problem is, when you see here, is that if you just go through BK7, that's the most common glass you can use in optics. The refractive index changes with the wavelength, that is with frequency. So that if you look at the phase after going through a piece of a Z distance in the glass, is that the phase will depend on omega, the angular frequency divided by the speed of light, the refractive index that depends on the frequency, and the distance you travel. So that you see as the distance increases, your phase will change for the different frequency components. So you can see in the next one that, in the next slide, that if you have a phase that's, in this case, is proportional to the refractive index and the distance, that phase can be developed to first order in the frequency shift respect to omega naught, that's the central frequency. You have the linear term here. And you can see that linear term, if you add the omega t term, that the phases will repeat themselves after A equals the time. A omega and minus omega t, but omega now is not the frequency, but the frequency shift. So that when you want to know what's the time delay for your pulse, the next one, click. Yes, advance. So you want the time delay. You see the time delay will be the derivative of the phase respect to frequency. That's the A coefficient we had there, which is different from the phase velocity. Sorry, you went too fast. Back to the previous one. Okay, so here you see that it's different from the phase velocity. So this is the time delay derivative of the phase respect to frequency. Now, if we have a more complex shape of the frequency dependent of the phase with second and third order terms, you not only have a different time delay, but you will have distortions. And that's what I will try to show you. So in the next, you can see the group delay now calculated per millimeter across the BK7 glass as a function of the wavelength. And you can see that the group delay depends on the wavelength. That means that if we look at the next slide, if we take the derivative again, that is the next, you can see that there's a group delay dispersion. That is, the group delay depends on the frequency. That means different frequency components will travel at different speeds, and then your pulse will be distorted because of that. We can look at the next slide, and you can see the third order term. And you can see, well, this is not that important at the center where the second order term was important, but it's very important in regions where the second order term wasn't that important. So you can see this is another distortion. So let me show you how this will affect your pulse. So in the next slide, you can see what I'm showing here is a typical situation where the phase has these three terms I mentioned before, but I will keep only for this first one on B and Z equals 0. So you only have the first order term, a group delay. So in this plot here, you have distance and time, and you can see that the intensity, color-coded, just moves linearly in distance as the time evolves. In the right panel, you can see the spectrum. In blue, the amplitude, the intensity of the spectrum, and in red, the phase as a function of frequency. And you see here just a linear term. And then in the bottom, you have a blue pulse. The blue pulse in time is the pulse we have at the beginning. And the red pulse is the one we have at the end at the distance 4 in arbitrary units. You can see that the pulse just kept the shape and just moved a certain distance. And you can see the field down. And you can see that the field, you just see the oscillations in the electric field. Now, in the next one, what I will do is change the A coefficient. Please, the next one. And you can see that A coefficient now is smaller, and then the pulse travels faster, but still, as you see in the right panel, without distortion. You see the same pulse just arrive faster to the other side. Now, let's see what happens if we add a second order term. B not equal 0. The next slide, please. Now you can see, as the pulse is traveling, you see that intensity is reduced and the pulse is broadening. You can see in the right panel here, I used an arbitrary parameter B, but you can see here the phase as a function of frequency, you have a slight curvature. It doesn't look to be a very large amount, but still, when you look at the pulse at the beginning, blue, at the end, red, you see that the pulse broadened and the intensity decreased. So this is what you get from the second order term. You click again, so we get the equations, and you can see what happens for a Gaussian pulse that has a pulse with tau naught. And you can see that after having a spectral phase, quadratic spectral phase with a B coefficient like the one here, the output pulse tau multiplied by the input pulse tau naught just depends in this manner. So you can see here, if B squared is much smaller than tau naught 4, that is, if B is much smaller than tau naught, then this will not have a significant effect. Conversely, if you want a significant stretching, you need B to be much larger than tau naught squared. For example, for an 100 femtosecond pulse, If b is of the order of 10 to the 4 femtosecond square, you will have a square root of 2 broadening of your pulse. Next slide, please. So now what happens with the third order term? You can see here a third order term. I set the second order term to 0, so you can see the effect only of the third order term. You can see the phase as a function of frequency in the graph that has an inflection point. And you can see down that the intensity just has a distortion after propagation. That's the red pulse. And you see that the oscillations seem kind of random. That's because you don't have a linear sweep in your frequency. So this is a type of distortion that will introduce satellite pulses. Depending on the sign of C, the satellite pulses will appear after the pulse or before the pulse. Okay, so let's go to my outline again. And now we'll go back to the next step. What I've been showing you is what happens in 1 dimension. Now, in 3 dimension, maybe intuition is not that good. And we have to go through it to build specific intuition to understand how we shape pulses going in 3 dimensions. So in the next view graph, you can see what I'm showing here is just a cone. This is a reflective cone. It's a cone, a mirror cone that will reflect a plane wave coming in. So click to advance, and you can see in the next here, you can see there 4 rays coming, impinging into that cone. They are at the same distance from the axis, and after impinging, they will be reflected. And you can click again the next one, and you will see them reflected at different angles and describing a cone. So the effect of this cone reflection is that you will have a superposition of plane waves distributed in a cone. And then let's go to the next one. And the next slide, what a superposition of plane waves distributed in a cone is what's called a Bessel beam. So let's assume a short pulse hits this mirror, conical mirror, and then it's reflected. Click for the next. Then you have this distribution of conical plane waves. And if you click again, you will see the equations. The superposition of plane waves, next, it's just what you can see there. You have a linear phase term, e to the I k z z, and a Bessel function for the radial distribution. Click again, and the intensity distribution next is just that distribution there. So you can see here that you have a phase that is omega over c z cosine theta. It's been projected. So if we take the derivative of that phase respect to frequency, we only have the frequency there in the linear term. So next slide. Yes, that's it. So you can see that the derivative of the phase respect to frequency now, which is the time delay, what you will have is a pulse traveling along the z-axis, but the time delay is smaller than z over c. That is, it's traveling faster than the speed of light. There is no pulse distortion. There is no second order term. But that's the next slide. What you can get here, if you make the distance divided by the time, that will give you the groove velocity. And the groove velocity is c divided by cosine theta, which can be much larger than c. This light travels faster than the speed of light. So you see, 3 dimensions is not intuitive. So if we go to the next slide, you might say, hey, yes, for the next one, please. You might say, hey, well, I was taught nothing travels faster than the speed of light. Was Einstein wrong, or there's something wrong here? Well, no, this is Maxwell's equation. This has to be relativistic. There's nothing wrong. So what's the trick? Let's look next one. let's look at this ray coming in. When you look at this ray coming in, that's the red ray. It's reflected as the dashed red, and then it crosses the axis at a given point. Now let's look at another ray, the green one. Next slide, please. Now the green one crosses at a different point. Now, if this is a plane wave or even a pulse, you click again the next one, you can see the phase front here in blue for the next slide. Yes, next. Yeah, here. You see that phase front in blue, both rays are in phase there and are in phase at the other blue phase front there. So you can see that when the red crosses the axis, the green one has a distance to be traveled yet. So next slide. So if we want to go to the point where the green crosses the line, it's a distance L from the point the red crossed. Next one. But the green had to travel a smaller distance, L cosine theta. So it's going to get there faster than what it would take moving along the z-axis. So next one. So if we block the beam at this point here, you can see that the red will make it anyhow because it's coming from the side. So the trick here is you will see a pulse moving along the axis, focused and moving along the axis at a speed faster than the speed of light, but the information is coming from the sides. That's why it's traveling faster than the speed of light. So this is telling us that we have to pay attention into what happens in 3 dimensions. Let's go to the next one. So now we'll go to a different situation. Next slide. Let's assume we have spectral angular dispersion. You can see here a diffraction grating. This yellow thing here is a pulse that is impinging in the grating. It's a transmission grating. And then the blue, when I say blue and red, I'm talking about blue is the high frequency components of my pulse, red is the low frequency components of my pulse, and green is the center frequency components of my pulse, regardless of the region of the spectrum we are dealing with. So what you see here is that there is angular dispersion. All wavelengths are not traveling in the same direction. So next slide, please. So when this pulse hits the grating, you see that it hits the grating at all locations at the same time because it's impinging at normal incidence. I did this example with normal incidence just to make it easier for the explanation. So the pulse will leave at the same position or at a different position at the same time. So next slide, what will happen with this pulse after leaving the grating, yes, next slide. Yes, that's it. After leaving the grating is that the pulse is tilted. You can see there that the pulse is tilted because it hit the grating at the same time in all positions and it has to leave it at the same time. So you have angular dispersion and a tilted pulse, and that means angular dispersion and tilted pulse are two things that come together. So let's forget about how we generated this angular dispersion, that is the grating. It doesn't matter how we generate it. So next slide. So we block that part of the drawing and we just look at the angular dispersion. So what you see here is that the pulse travels tilted. And what does this mean regarding the time delay and the time delay dispersion? Let's assume this pulse has to advance to next slide. So next slide, please. So you see the pulse advance from one position to another one. And so now let's see how this pulse is built. It has contributions from the blue, from the red, from all the spectrum. Now, where does the red come from? Okay, next slide. The red comes from here. You can see because of the direction it's traveling, that the red, so if we look at the next slide where the blue is coming from, so next, you see that the blue has a smaller distance that it has to travel to get to the new position. So you build this pulse with red coming from farther away from the blue. That means the blue is traveling faster than the red. So because we have angular dispersion, we have a blue traveling faster than the red. That is high frequency traveling faster than low frequency. And that's regardless of the sign of the dispersion. Let's go to the next slide and see how this appears in the equations. So next. So you can see here that if we look at this propagation along the z-axis, that is x and y equal to 0, we look at the phase that I wrote here, phase as a function of the frequency and the z direction. It's omega over c z times cosine theta, just like in the cone, but now theta depends on the frequency. So now we have dispersion because our phase is not linear with the distance. So let's go to the next slide. If we take this phase term, and I write omega now as the shift respect to the omega naught, that's the central frequency, so that omega equals 0 is the central frequency, you can see that it has a dependence with omega that's not linear. So if we take the derivative now, next slide. Okay, you see it has two terms, one with cosine theta, one with sine theta. Now, if we evaluate this at theta equals 0, the sine theta goes to 0, cosine goes to 1, and we get z over c. So this time delay is just a pulse traveling at the speed of light. But what happens with the time delay dispersion, the group delay dispersion? That's the next slide. So next. So you see that if we take the derivative respect to frequency and then we evaluate at theta equals 0, we get this term here, minus omega naught over c, the distance, and the angular spectral dispersion squared. Let's go to the next slide. We just look at this term here. And you see then we have a group delay dispersion, that is different colors are traveling at different speeds. And this is always negative because we travel a positive distance, omega over c is positive, and the angular dispersion is squared. So regardless of the sign of the angular dispersion, this term will be negative. So let's go to the next view then. So next. Okay, so what do we have here? The other thing we want to look at, we said before, if we have angular dispersion, you have tilt. So let's see the phase as a function of x at constant z. If we are at constant z, the term we get is not the cosine term, but the sine term. And then if we take the derivative of this, that's the group delay. Let's look at the time delay, sorry. Let's look at this next one. So next. You see that the time delay depends on x, is proportional to the lateral displacement. That is, the time delay depends on the lateral displacement. That's a tilted pulse. It doesn't arrive to the z equal constant plane at the same time at all positions. It's tilted. And the sign of the tilt depends on the sign of the derivative of the angular dispersion, the derivative of the angular respect to frequency. If you change the sign, you change the sign of the tilt, but you don't change the time delay dispersion. So next, how do you use this to your favor? Let's go to the next one. So putting angular dispersion to work in your favor, next slide, please. What you do is, you have group delay dispersion. And if you wanted to print in your pulse a certain dispersion or correct for it, this is a linear term. If it comes with dispersion, you can correct, or you can pre-correct for future distortions. Like, for example, you go through large chunks of glasses that will distort your pulse, like microscope objectives, you can pre-compensate. It doesn't matter if you can do things in any order because this is all linear. So what you do is you place a second grating parallel to the first grating. So you see in between the gratings, you have this tilted pulse propagating with angular dispersion that will, with a blue traveling faster than the red and getting ahead of it. When you go through the second grating, all your beams now are parallel. You stop the angular dispersion. And then what you get is a blue coming before the red. Now, next slide. The problem you might have with this setup is that you can have a spatial chirp. That is, different colors are traveling at different directions, and if your beam is not wide enough, you will have a lateral walk-off of the different colors that could be significant. I mean, if your beam is much larger than this walk-off, you probably won't notice it, but otherwise, this is a problem. So how do you solve this problem? Next slide. You just bounce that beam back over itself. You can use a roof prism, so you go above the beam, and then you retrieve all the transit back through to the first grating, and you recompose all the colors overlapping at the output. And you double your dispersion, because now you change the sign of your dispersion, but the group delay dispersion doesn't depend on the sign. So you recover all, you cancel all the spatial chirp, and you recover all the beam, all these frequency components at the same axis. So let's go to the next slide. So now, this is a funny situation. For almost a decade, from Tracy's compressor original paper you can see at the end, people thought that the prisms wouldn't work because you can notice that prisms disperse the other way around. Higher angles for the blue, smaller angles for the red. So it looks as if the blue is going through a longer distance. But despite of this, it just changes the angle of the tilt. But the blue is always going to get to the other side faster than the red. You use a second prism anti-parallel to compensate for the dispersion, and at the output you get the group delay dispersion that you can change. The prisms have two particular advantages. It has very low insertion loss if you work at Brewster angle. The two prisms can have a less than 1 per 1,000 loss. And the other one is that if you move one prism in the along its axis, you introduce more and more glass into the path, so you can control the total dispersion just by changing the amount of glass you're crossing, because the sign you're getting here has the opposite sign, if you remember, as the one you would get from a glass. The problem with prisms is that the angular dispersion is small. Let's put some number to this. Let's go to the next slide, where I'll give you an example. So here you see gratings and prisms are similar but different. They are similar in that you get blue before the red. They are different in the angular dispersion sign. They are different in the sense that with the prisms you can control the total amount, not by changing the distance, but also by changing the amount of glass you are crossing. And they are different because of the amount of dispersion you can accumulate. So let's go to the next one. The next slide, I'm just showing you a few examples of the order of magnitude of the number. Just different central frequencies, 800, 1000 nanometers, 500 nanometers at first column, different group densities. You just choose a grating that's suitable for that wavelength, and the angle of incidence where you get a high efficiency. And you can see that the group delay dispersions in femtosecond squared divided by centimeter, that is, you have to multiply this by the distance between the gratings. And you can see these numbers are huge. From tens of thousands per centimeter, imagine you place your gratings 10 centimeters away, and you're getting numbers of the order of 10 to the 5 to 10 to the 7 femtosecond square. So that can be a huge chirping for chirp pulse amplifications, or just a nice compensation for a lot of glass in your optical system if you want to recompress your pulse back after microscope objectives and so forth, tube lenses and whatever you are using in your experiment. Now, let's compare this. Remember, hundreds of thousands to millions of femtosecond square. Let's compare that with the next one with the prisms. Thank you. So with prisms, you can see it depends on the material. You see here in blue is calcium fluoride, red is fused silica, and the other two are just dense flint glasses. These are prisms. And you can see that depending on the distance between prisms, you get, let's say, 100 femtosecond square per centimeter. So if you place them 1 meter away, or let's say half a meter, and you double pass the system because you want to compensate for lateral walk-off, you get 10 to the 4. 10 to the 4 femtosecond square is more than enough to compensate for a microscope objective with a lot of glass in it. So this might be a nice way to compensate for that type of experiments, but that's about the amounts you can get. And what's nice about prisms, you can place them inside lasers and the insertion loss is negligible. So let's go to the next slide. Now, we said that you can have walk-off in your system. Now, let's assume you try to compensate for that walk-off, that spectral walk-off. You can see here, blue, green, and red, not centered at the same position. And then in your experiment, you're going to focus this beam into your sample. What will happen is that from focal plane here at the beginning to the focal plane at the end where you place your experiment, there is no phase difference regardless of which of these blue, red, or green paths I take, because that's what happens when you go from focal plane to focal plane of a lens. There's no phase difference. That's why it's a focal point. But what will happen is that this spatial chirp at the beginning will be translated into angular dispersion at the focal point. That means your pulse will be tilted at your target. So this could be important or not, depends on your experiment. A multiphoton fluorescence, this doesn't matter. But if you're doing pump and probe, you might have a different tilt in your pump and probe beams, and that will distort your experiment. So let's go to the next one. The next slide. This is the reverse situation. Let's assume you don't have properly aligned your prisms or gratings. So you have a residual angular dispersion. You didn't exactly cancel the dispersion from the first grating with the second one. You have a residual dispersion. What happens after you focus, again, the phases are the same on all these paths, but your beams, different colors will be centered at different locations. So you will have a spatial walk-off, delta x, that will be the angular error multiplied by the focal distance. And this number has to be much smaller than your beam width at your focal point. Otherwise, you will have a reduced bandwidth and your pulse will broaden. So you can see that these are things that you have to take care when you're planning an experiment. These things translate after focusing in different manners, and they are just conjugate ways. Spatial dispersion gives angular dispersion gives spatial dispersion. So let's go to the next slide. So as I mentioned before, and this is the next one, there are situations where you want to change the sign of your dispersion. Remember I mentioned the chirp pulse amplifications. I want to broaden the pulse. I imprint in the pulse a huge dispersion, but then I have to put a dispersion of the opposite sign to recompress it. And as we said, gratings always, or angular dispersion always gives negative group delay dispersion. So, is there any way to change this sign? Yes, let's look. Next slide. You can change the sign. Next, please. If you make Z negative. So this is optics. You can make a distance negative And in the next slide here, I'm showing you how. If we look at this 4F, this is called 4F telescope. It's two lenses placed with sharing focal plane. Both have the same focal distance. And you can see now that from focal plane to focal plane, from the first one to the last one, there is no phase delay. All paths are equal. That means that the blue, red, or green, they all travel the same optical path to get to the other focal plane. So how do I get this angular dispersion here? Next slide. If you place your grating at the focal plane and the other one at the other focal plane, you see that this one has been inverted because the telescope inverts your image. So the second grating here is the image of the first grating here. After recombining all your spectrum here, there's no group delay because all paths are equal. This is equivalent to a zero distance travel optical. So let's go to the next one. If I move a grating, next slide. If I move the grating back, you can see this region in space has negative delay dispersion because it has a positive distance. That means your pulse, the blue, will come after the last grating ahead of the red. Now, next slide. If I move the grating in the other direction, next. Okay, that's it. If I move in the other direction, no, what you see, there's a lack of distance here where the pulse should have traveled to keep zero equivalent distance. This means this is a net negative distance. This is the way you get negative Z. This pulse lacks a travel distance Z between the focal plane and the grating to get zero at the end. So this is not zero, this is negative. Let's go to the next one. You can move the second grating too. And here you can see the second grating. Now you have a nice negative distance traveled. So this compressor, this is a stretcher. This is a stretcher that exactly matches the grating compressor. This has a negative distance. When you go through a positive distance, you exactly match to all orders. So this is a pair you use for shear pulse amplifications. Negative, or eventually if you need a negative contribution, because what can happen? You're working in the near infrared beyond the inflection point where the contribution from your material can have the opposite sign. We said before that the glass has positive group delay dispersion, but if you go above 1.3 microns or so, glasses introduce negative dispersion. So if you want to compensate that, you have to, like an optical fiber, you have to use something like this. Let's go to the next one. So, no, the other thing is, we said that the group delay dispersion depends on the angular dispersion squared. So if we magnify the angular dispersion, this telescope with two different focal distance, you have an angular magnification. You can clearly see that the angular magnification has been increased by this telescope. This means, as you see in the bottom, that the group delay dispersion has been increased by the angular magnification squared. And this can be used to magnify your dispersion. You can see a nice example in the next slide. So the next one is just an application of this. So you can see here, this is just an example of a microscope for multiphoton microscopy where you have a grating at the camera plane, then you have a tube lens, an objective, and then the sample is the last focal distance. Let's assume you have a 50 times magnification in this telescope. You have a 2,500 times magnification in the group delay dispersion. What you get with this is you image this grating at the focal plane where the beam is recompressed at the focal plane, but very rapidly in a huge amount. In 1 micron, your pulse has been broadened so much that you don't have any more, because remember I said multiphoton absorption depends on your pulse width. If it has been broadened so much, you lose your signal, so you only get signal from the focal plane. So this is just a nice application of how you can use magnification. With this, I finish the 3D section of my talk. Let's go to the next transparency. So I will just talk about other shaping mechanisms that do not rely in 3 dimensions. And let's go to the next one then. One of the things, next slide, is interference. The first example of interference is the Gir-Tournois interferometer. It's like a Fabry-Perot, but you have 100% mirror on one side. So all the frequencies are 100% reflected. And you see in the right side a graph at a given distance, L, like in Fabry-Perot, the reflectivity and the distance between mirrors are your control parameters. And you see as a function of the reflectivity and the wavelength for a given distance, in this case 21 micron separation between mirrors, you can see that you can get huge numbers in the group delay dispersion, picosecond square, but over a very narrow bandwidth. So this can be useful for picosecond pulses. I just included it for completeness. And let's go to the next slide, just to make you aware that interference can spoil your pulses. So you can see here, if you have to choose mirrors for your experiment, you have to check the group delay dispersions from the mirrors from the manufacturer. Here you have examples of mirrors designed for low group delay dispersion. These numbers, less than 20 femtosecond squared, are numbers very low. But if you go close to the edge of the mirrors where the reflectivity still is very high, the group delay dispersion can be huge. You have to take care, as you see in the right side plot, on the angle and polarization effects. So mirrors are things that you have to take care of. And if we go to the next slide shows an example of mirrors specifically designed to get group delay dispersion. These are called chirp mirrors. And you can see here in this cartoon at the top that the blue, you have a mirror that has spacing between layers changes as you go deep into the mirror. You have hundreds of these layers. And you can see that the blue is reflected on one side of the mirror and the red goes in deeper. If you come from the other side, the blue goes deep and the red is reflected very fast. So then you have a time delay due to this, and you have here the group delay as a function of wavelength, and the slope of this will give you an idea of the group delay dispersion. In this case, you have 175 minus 175 femtosecond squared. So if you want to compensate for, as I mentioned, a microscope objective, you need like 50 bounces. And those 50 bounces, as you see in the right, are obtained just by bouncing between two mirrors many times, and you control the total amount with the number of bounces. So this is a way to control dispersions without using gratings or prisms. Let's go to the next one. Another way of doing this control, a fancier way, next slide, is what I call the Wiener shaper. And the Wiener used this zero-order dispersion system I mentioned before, but at the focal plane here in the middle, place a phase filter. It can be an amplitude filter. And the phase filter could be a modulator, so you can change it. No, sorry, the one before. The slide before this one. Okay, so the phase filter here in your focal plane will tailor your phase filter in your spectrum because different frequency components go through this phase filter at different locations. So after you recombine your poles, you can just imprint the phase or eventually the amplitude, whatever you want, to shape the poles to whatever shape you want or to correct for distortions before. Next slide, please, and that's the last one. So the other device that you can use is using acousto-optic devices. This is a birefringent acousto-optic material where the blue signal here is the acoustic wave, S, that depends on time. You have an input pulse, E input, that depends on time. And at the output, what you get is the convolution. You couple nonlinearly with this birefringence filter, this acoustic wave with the input pulse, and at the orthogonal polarization, you get a pulse that is a convolution of the input pulse with the acoustic wave but scaled in time by the difference in the speed between the two. With this, next slide, please. You can get, next, yeah, very fast, that's it. Very fast modulations, very fast changes in your modulations. The efficiency might not be that large, maybe 50%. Dynamic range is quite large, 100 to 1. And you can manage several picoseconds with this and shape your pulse. With this, I come to my last transparency, please, the next one. So just the references. So I'll go to the next slide just for a few seconds. Well, you have just some references on the different topics. So you can go back to this recording and pick them up. The next slide, please. And then you can take this other reference to the other topics I mentioned. And finally, the last one, I just want to thank you. Last slide. I just want to thank you for the patience and sorry for the inconvenience. I don't know why that PowerPoint just went by itself. So thank you very much, and I'm open to questions. Or you had at the beginning my email, so you can ask questions there.
All right. Thank you so much, Oscar, for that informative presentation. In the interest of time, we're a little bit over. And again, thank you in the audience for your patience. We will bypass the live Q&A. However, please submit your questions and we will get them answered. So thank you again, Oscar, for your presentation. And thank you, audience, for attending. Our next webinar will be on November 13th with a Thorlabs physical optics engineer. We'll discuss advancements in surface-enhanced Raman spectroscopy for commercial applications. You can register for this webinar by clicking the Register Now button below or on our website. Thank you very much for your attendance. We hope to see you again.